Sir, shall we start, sir?
Yes.
So I will formally introduce you to the students, then you will start, sir. So, good afternoon to everyone. I welcome all of you to the 28th lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Professor Soumitra Banerjee from ISET, Kolkata. I don't need to introduce Professor Soumitra Banerjee to the nonlinear dynamics community in India. However, in view of the students assembled here, I wish to read out his scientific achievements in a very brief manner. Professor Soumitra Banerjee is basically an engineer. He did his PhD in electrical engineering in IIT Delhi and started his academic career in IIT Kharagpur. About 12 years ago, he moved to the newly started institute ISET, Kolkata. He won the highest scientific prize given to the individual by Government of India, Shanti Saurabh Bhatnagar Prize, in 2003. Besides the fellow of 3 academics, he is a fellow of Indian National Academy of Engineering, the World Academy of Sciences, NACI Fellowship from National Academy of Sciences, and JC Fellowship, and he has many more awards. His current research interests are theory of non-smooth bifurcations and the switching electronic systems. He has worked extensively on nonlinear phenomena in power electronics, and his H index is very high. It is 68. Besides all the mentioned ones so far in the above, Professor Soumitra Banerjee played a very crucial role in setting up NCNSD, then CNSD conference series in India. This conference brings various groups working in the area of nonlinear dynamics on a single platform to exchange views and to report their research findings. The meeting covers all areas of nonlinear dynamics and being organized once in 2 years in various places in India. This conference started in the year 2003 and still being organized. Since he is the main organizing man, he used to appear in every meeting since 2003, whatever be his commitments in other matters. In fact, I used to meet him in the meetings. It was exactly 2 years ago I visited his institute when I was attending a conference in the University of Kalyani, West Bengal. It was a nice trip to that institute. I can keep on speaking about him. To keep the time schedule, now I hand over the session to Professor Soumitra Banerjee. Over to you, sir.
Thank you. Thank you, Professor Sandilala. Well, as you have heard from him, I work in various areas in nonlinear dynamics. And today I will be talking about an area in which I have not, I did not do any work earlier. So this is something that we are exploring only recently. Let me switch on the presentation. Yes. Can you see the presentation?
Yes.
Yeah. So here we are talking about the dynamics of quantum systems. Now, first let me give a brief outline of what I will be talking about. When I was doing work on mainstream nonlinear dynamics, one of the things that I focused on are the non-smooth systems, and one typical example of a non-smooth system are the impact oscillators. I'll come to what these are, where there is some kind of an impact. Now, in this particular work, we'll talk about the quantum version of that impact oscillator, and we'll talk about various ways of analysis, the Wiener distribution, overlap integrals, and various tests for chaos. And we will do it in stages. In the first stage, we'll take an oscillator without forcing or damping. Then we'll introduce forcing. Then we'll introduce damping. And then I'll talk about something called a soft impact oscillator. So let's go on. So what are impacting systems? Wherever there is a possibility of an impact, two bodies, two hard surfaces impacting with each other. Now that impact itself is a nonlinear phenomenon. So these are very common in engineering, and that is why these have been studied since the 1980s. and quite a lot of things are known already. Now, we take a very simple model of such a system where you have a mass spring damper system with a forcing here, and there is a wall. So the mass, as it oscillates, has a possibility of hitting the wall, impacting the wall, and it has been observed that various nonlinear phenomena, including chaos, develops at a very typical phenomenon, which is grazing. That means when the mass just grazes this wall, slightly higher velocity will make it impact, slightly lower velocity will not make a contact. That grazing condition is what gives rise to various nonlinear dynamical phenomena. There has been a great deal of study on that. And it has been shown way back in 1991 that what actually happens is, if you cast the problem in the form of a map, that means you look at only the what is known as the stroboscopic sampling. There is a forcing function, a sinusoidal forcing. So you observe it at every cycle of that sinusoidal forcing. And if you observe that, then Nordmark showed that the map will have a form like this. This part is for the non-impacting situation, and this part is for the impacting situation. And you notice this term, a square root term here. Now, if you want to look at its Jacobian, then the Jacobian element will be a 1 by square root. The derivative of square root is 1 by square root. So the x goes to the denominator. And as a result, as we approach x, that particular Jacobian element reaches infinity, goes to infinity. So that's why it's called a square root singularity. And this kind of a system has a bifurcation diagram, something like this. This is when you are varying a parameter, it is approaching the grazing condition, and this is where it's grazing. And after that, instantly, chaotic behavior develops, and that then goes through various periodic and chaotic orbits. It is easier to understand that in terms of the one-dimensional map, because you can then draw a graph. Here is the square root term, and the infinity in the slope is exhibited here. Right? Now, what will happen is that if you take a small interval on the x-axis here, it will map to a small interval on the xn+1 axis. But if you take a small interval of x here, it will map to a very large interval in the xn+1 axis. So there is a stretching. In fact, infinite stretching. It's called the infinite local stretching, and this is what is responsible for the nonlinear phenomena that we observe. And it is easy to figure out why, because if you start from an initial condition and the orbit just grazes, then if you move the initial condition slightly, then it will impact and it will instantly jump to the negative value of the velocity, and it will go back. So there is a large change here. So a small change here leads to a large change. As a result of, there will be a large change in the final condition. So that is what gives rise to that singularity. And it has also been experimentally, this kind of systems have been experimentally investigated. And it has been found that this is the bifurcation diagram that was obtained experimentally. And as you see that close to the grazing condition, there is a narrow band of chaos. That is what develops. And if you look at its Poincare section, it has a fingered structure, so on and so forth. These things are well explored. Bottom line is that, okay, why does this happen? There's also some interesting story behind it. Since you are from nonlinear dynamics background, you find it interesting. We explored why does it show this narrow band of chaos. We found that as you have this non-impacting orbit, as you change the parameter, in this case the frequency, parameter is varied. Unseen and unobserved, there are a couple of unstable periodic orbits that are born here, and that continue to coexist with this, and then at the grazing point where the actual orbit, the main orbit grazes, these two orbits also converge on that. And as a result, every initial condition in the neighborhood of that is repelled away, and that is why you have instant occurrence of the chaos. Okay. Interesting. But for our purpose today, we are not really looking at this. The only take-home message from the classical part is that the impact oscillator exhibits chaos close to the grazing condition. Now we ask, what will happen in a quantum version of that? Now, systems which are classically chaotic, what happens in the quantum version, many people have explored that. But normally the way they explore it is by looking at the eigenvalue statistics or eigenvalue different statistics. But here we will look at the evolution of the system itself. So in order to do that, we will first start with what the kind of quantum mechanics that you have studied. This is basically a conservative system, right? So in order to make it conservative, we first drop this damping element, and we also drop the forcing term. So it is basically harmonic oscillator. What remains is nothing but a harmonic oscillator, only with a wall. That's all. And we will try to explore what happens in the quantum domain. Look at it, what happens in the classical domain. In the classical domain, if you start from an initial condition, it will go and then hit the wall and then come back. Here is the momentum axis. Momentum instantly reverses and comes back. But the orbit is periodic. Okay, so if you have a system without forcing and damping, the orbit is periodic. But if you start from a ball of initial conditions, a collection of initial conditions, then that will go ahead, and then as it hits the wall, it will stretch. So there is stretching, but there is no folding. So this is what happens in this case. So now let us look at the quantum version. The quantum version is actually surprisingly simple, because we have all studied the harmonic oscillator. It has the harmonic oscillator potential. Only at some point at the X wall, it is terminated by an infinite square well. That's all. You have studied the harmonic oscillator, you have studied the infinite well. So just put these ideas together. I hope you'll find it easy to understand what I'm talking about. So in the left side of the X wall, it is just the harmonic oscillator potential, and at the X wall, it becomes infinity. That's all. Now we have to start the initial condition, and normally you will start the initial condition like you stretch the spring and you will release it. And akin to that, here we cannot talk about a definite position, a definite momentum, because it's a quantum system. The nearest we can have is a Gaussian wave function, wave packet, centered at some place, say x0. Okay, so x0 is to this side and x wall is to that side. So if the x0 is equal to x wall, then the classical system would have grazed. Okay, and we therefore start with this kind of a initial state. How do we time evolve? We basically time evolve using the time evolution operator. Probably you have studied that in the quantum mechanics course. So the initial wave function is psi x at time 0. That pre-multiplied with a matrix, the time evolution operator, gives the wave function at a later time. And what is this time evolution operator? It is nothing but an exponential matrix where the Hamiltonian operator is sitting here. Now the Hamiltonian operator is basically a combination of the kinetic energy part and the potential energy part. And in order to cast it in a programmable, computable form, this has to be a matrix, this has to be a vector, and therefore this has to be a vector. So this has to be cast in a matrix form, and for that this has to be cast in a matrix form. And what we do is to divide the x coordinate into a number of segments, And in the middle of each segment, the position is x1, x2, x3, and all that. And at those positions, the wave function has the value psi x1, psi x2, psi x3. So here is a vector, and psi is also defined as a vector. Now, the double derivative by the finite difference formula can be written like this. And if you use this, then the kinetic energy part, where there was a double derivative, that takes the form of a tri-diagonal matrix. And the potential energy part is a diagonal matrix. You can simply add them up, obtain the Hamiltonian as a square matrix, and then using the MATLAB's EXPM function, exponential matrix function, you can obtain the value of this. And therefore, using that, you can evolve any initial wave function. Let me tell you that whenever we do something, we always try to do it by more than one method so that we can cross-check whether our algorithm is working correctly or not. So here also we did that. This can be done. This can also be done by decomposing the initial wave packet in terms of the eigenfunctions of the system, and then evolving by multiplying by the phase factor. So there are various ways of doing this time-dependent Schrodinger equation calculation, and we have just taken one of them. That finally worked fine. Okay, now let's see the computer simulation results. Suppose the wall is far, but since the wave function is a distributed thing, it's not in one place, therefore, what will happen is that it will have some interaction with the wall, and as a result of which these wiggles will develop, right? Now, if it is at the position where the classical impacting system, impact oscillator would have grazed, then you see that those wiggles become more pronounced, they become accentuated, and you would notice that we now have an evolution of the wave function. We're plotting actually mod psi square because psi is a complex number. You notice that this is evolving in a aperiodic manner. Similarly, if it is closer, that means it is impacting in every cycle, then also it evolves, the wave function evolves in a aperiodic manner. But if it is right in the middle, that means the harmonic oscillator wave right in the middle, you have this wall, then it is an exactly solvable problem. And because it is exactly solvable problem, it is periodic. So you see that in the quantum analog of the impact oscillator, we have both periodic orbits as well as chaotic. I would not say orbits, it is basically periodic or chaotic evolutions of the wave function. Now, we are normally used to seeing things, we nonlinear dynamicists are usually, we are comfortable with seeing things in the phase space. And here the phase space will comprise the position and the momentum. And there is a representation, Wiener distribution, which allows you to represent that, but that gives you a quasi-probability distribution, not exactly a probability distribution, it can go negative. So when we plotted the Wiener distribution in the position momentum space, normally a classical system will have a point that will move in that px space, but here a blob will move, and that will now evolve and take new structures. So the structures will evolve. And if it is at the grazing condition, then structures become more interesting and intricate. If it is closer to the if the wall is closer, then also it has those interesting structures developing. Noticeable is the fact that the evolution of the structures is also aperiodic. But when the wall is at 0, that is in the middle, then it again becomes a periodic behavior. This is actually our check that our algorithm is working all right, because this can be exactly solved. You can also do that in 3D. You can see the 3-dimensional evolution of the Wiener surface plot. This is the case of the wall being placed as the grazing condition. This is where the wall is placed at the relatively more closer, and this is where the wall is placed at 0. Okay, so the bottom line is that in this system we have an evolution of the wave function, and that wave evolution, when seen in the Wiener distribution, shows evolution of a structures in the XP space. But then we are not used to handling like this. We are nonlinear dynamicists always like to handle time series. So somehow we need to cast it in the form of a time series. But the problem is that quantum mechanics does not allow a well-defined trajectory in the phase space. So what do we do? So that becomes the characteristic dynamics a bit difficult, and there have been other papers in which people have used the expectation value. Expectation value of the position, expectation value of the momentum, and things like that, representing the state. But we did not do that because the expectation, one can have the same expectation value for different wave functions, and so we tried to find out something else, and we rather homed on to overlap integral. Here we are using the overlap between the initial state and the state at time t. So how much there is overlap? This is the overlap integral, or its mod. So that is what you're using. It will be a time-dependent quantity. It has an exact value, it has a positive value, and it does capture periodicity. So from what we have is a complex valued wave function. It's evolving. From there, we extract a real valued time series, which we can subject to various tests. That's what we do. Now, when we do that, then this is the time series plotted. Let's start from the bottom. If the wall is placed at infinity, it is nothing but a harmonic oscillator. So you have a sinusoidal oscillation, which is expected and which is happens. If it is very far away, then also it is not very different from what it was for the wall at infinity. But as the wall is brought closer, then there would be interaction with the wave function, and then there would be this aperiodic behaviors developing, and at grazing it is very, very saliently aperiodic. When it's impacting, it's still so, but when the wall is brought at 0 position, then it is again periodic with a periodicity twice the period here. Well, so we are interested in these cases. What is actually happening? So we looked at the time series and we expanded it, zoomed into it, and we find that as we zoom in and in, it still has some structures. So the time series itself has sort of a fractal structure. But when we did a delay coordinate embedding, which is very common in nonlinear dynamics, you take one time series, you delay it and create another time series y, you delay it and create another time series z, and then you plot it. This is very standard. There is a theorem that says that if you recreate a multi-dimensional phase space from the one time series, then the topological character of the system will be preserved. But here we see no structure is evolving. We don't see any structure. It's just like a messy ball of wool. So this particular attempt of ours did not really bear fruit. Then we asked, is there any sensitive dependence on initial condition? We didn't really expect because the system is linear, but nevertheless we checked. Now in this case, the initial condition is the initial wave function. Therefore, two nearby initial condition would be two nearby initial wave functions. So if you start from two nearby initial wave functions, this graph or the graph of the overlap integral shows that they remain close to each other. Even though they sometimes move away, but still they remain. There's no sensitive dependence on initial condition. And there is also a 0-1 test for chaos. It will be out of the scope of this talk to explain what the 0-1 test is. Probably you already know. It is we do some manipulation using a time series, and the result of that computation is if the time series represents a periodic orbit or a quasi-periodic orbit, then the output will be 0. If it is chaotic, the output will be something close to 1. So it is a very 0-1 test, as it's called. Very clear distinction between a regular behavior, which is a periodic or quasi-periodic behavior, and a chaotic behavior. And here it is clear that it is not chaos. So the conclusion is that in this system that we explored, it is not chaotic. It's not expected also, because the classical system is also not chaotic. The Fourier spectrum, the frequency spectrum, shows that there are many frequencies. So I would categorize that as a quasi-periodic behavior with many frequencies. And now let us go to the impact oscillator with forcing. We are slowly introducing things, making it more and more closer to the practical system that we started with. Here, in addition to what it was, there would be a forcing function here, which is a sinusoidal forcing function. And as a result, this harmonic oscillator potential will oscillate like this. And we start from the same initial Gaussian wave packet. Well, in this case, if you look at the classical dynamics, we find that it does go into chaos abruptly at the grazing condition. This is the orbit where it is not grazing, and here is the wall, and I'll allow the wall to go closer. The moment it touches the orbit, it becomes chaotic. Again, if you recede the wall, it becomes again a periodic behavior when it goes away. Look. Now, if you start from a ball of initial conditions, then you see that unlike the last case, it does stretch as well as fold. So we do expect there to be chaos in this case. Now let us see what happens in the quantum domain. In the quantum domain, as you have already seen, the probability density function, the mod psi square, oscillates in a aperiodic way here. And here is the Wiener distribution. Here also you see that it is evolving, structures are evolving in a non-periodic way. And here is the overlap integral, which varies between 0 and 1. You find that this is also a aperiodic structure. Now, when we subjected this to the 0-1 test, we found that for some ranges of the forcing amplitude, it is 0, which means that it's not periodic. For some ranges, it is close to 1. But for most ranges here, it is somewhere in between, which is sort of a signature of strange non-chaotic orbit. We are not yet completely sure, but I would say that it has some of the signatures of a strange non-chaotic orbit. And if you look at the Fourier spectrum, then you see that it has many frequencies, but as you zoom into it, you see that at every range there are frequency components. So the frequency spectrum itself behaves like a fractal. And is there sensitive dependence on initial condition? No, obviously not, and it is therefore not chaotic. We can also plot bifurcation diagrams, even for quantum systems. So here is the classical bifurcation diagram, where, as you know how to draw the classical bifurcation diagrams, we stroboscopically observe the state, and then for a long time, and then we plot. So if there is a aperiodic orbit, there is smudge of dots, and here you see there is a smudge of dots, and this is the grazing condition. So beyond that, there are smudge of dots, chaos. Now, when you do that, for the overlap integral, we do see in this case a smudge of dots. So it has that aperiod behavior. And here in this case, we have actually averaged out the mod psi square and plotted it. Here also we see a behavior somewhat similar to the classical behavior. So there are some characters akin to the classical behavior that we see in the quantum domain also. Now, so far we were dealing with, first we dealt with a system without the forcing and damping. Then we introduced the forcing but no damping. But now we need to introduce damping. Now, damping is not really an integral part of the normal quantum theory. But it is possible to introduce damping by introducing interaction with an environment. So that is what we have done. So we have considered a system with the Hilbert space curly H. With, in this case, the representation has to be in terms of the density matrix. So density matrix rho and the Hamiltonian H for the system. And there is an environment with its own Hilbert space, its own rho, its own Hamiltonian, and they are interacting with a term like the interaction term Hi with a strength alpha. So the total system will be this with a subscript of capital T. So the total Hamiltonian will have the tensor product of the Hamiltonian of the system with 1 and 1 with the Hamiltonian of the environment plus this interaction term. So that way we define the Hamiltonian of the whole system, and then the density matrix will evolve according to this equation, which you can solve, and then finally we extract the information regarding the system by the partial trace. That way we extract, and then what we see is this. In this case, we have to use the expectation value because we do not have a wave function. We have the density matrix. So we have plotted the expectation value of position, expectation value of momentum, and it does show an orbit, and that orbit is non-repetitive orbit. Here we have the same evolution of the wave function, mod psi square. So here is the expected momentum as it evolves. Here is the expected position as it evolves. Both are aperiodic behaviors. And if you look at the frequency spectrum, you would notice that the number of frequency components have drastically reduced. So this is one effect of the damping, environment introduced damping. And if you increase the amount of damping or the interaction term alpha, then you see that it sort of smudges out. It loses structure. But I must say that we do not have great deal of confidence on this computation after a certain time, because higher energy components start having significant strength, and so the subdivision of the X space that we did might not suffice. So I'm showing this as sort of a tentative result. We need to wait for more time for this computation to be reliable. And in this case also, it is not sensitively dependent on initial condition. Great. So we have done the 3 cases. Now there is one additional case, which is the soft impact oscillator, which is also very common in engineering, where here is the wall, the rest of the system is the same, here is the wall, but the wall is supported in the back by a spring. So it is a soft impact. So when the mass impacts, it has a possibility of pushing it backwards. So the mass can take a position which is behind the wall. So in this case, it is not difficult to, in this case also it has been explored to great depths, both theoretically and experimentally. It has been found that as the K2, this term becomes more and more stiff, more and more higher. It becomes almost like a hard impacting system. And all the behaviors that we saw earlier, that happens, the chaos happens. Normally, in this case also, you have chaos following the Gracie condition. The quantum system would be actually easy to simulate because it is the same harmonic oscillator potential up to the position of the wall, and then it is another parabolic function because it's like this. So it is not difficult to simulate this, and when we do that, we find that its behavior is, it's going a bit beyond the wall, yes, but it is interacting and it is developing those wiggles, and this is what was expected. But now, in this system, another possibility exists, which did not exist in the earlier system. What is it? You'd notice that here this is the wall, and the wall is a macroscopic body. And therefore, a quantum particle is coming in contact or interacting with a macroscopic body. It is as if the macroscopic body is observing the particle. Now, we know that when that happens, there is a possibility of wave function collapse. So the wave function might collapse. The problem is, in the whole structure of quantum mechanics, the collapse of the wave function is the least understood part. The mechanism of the collapse, we do not know. Has anybody seen a collapse happening? We don't know. And what is the under what condition would it collapse? What would it collapse into? All these things are pretty much unknown. So what we did was, we guessed. In science, it is called postulate. So we postulated 4 different types of collapse. So what we did was, we postulated that if the probability of finding the particle beyond the position of the wall exceeds a fraction, say r, that is, this number is exceeding r, then the wave function collapses. And where does it collapse? It collapses at the position of the wall. So this is what we first postulate. See, let's see the behavior. See here, right at this point, when it reaches, it will go to a collapse. Then the postulate 2. In this case, it is the same. Like if the probability of finding the particle, that means the mod psi square integrated in the other side of the wall's position, that from the wall to the infinity. So the probability of finding the particle beyond the position of the wall exceeds a fraction r, but in this case, the fraction r is not a constant. It is a random number between 0 and 1. So it can vary. So when you allow that to happen, then see it collapsed, and again it evolves according to the Schrodinger equation, and then it again collapsed. It collapsed. See, again it will evolve. So it is a combination of evolution according to the Schrodinger equation and non-unitary collapses. So it is evolution is a combination of these two processes, unitary and non-unitary. Third postulate is where if the probability of finding the particle beyond the position of the wall exceeds a fraction, but in this case, it collapses not to the position of the wall, but it is given by the Bond's rule. That means where depending on the shape of the wave function, wherever it has a non-zero mod psi square, depending on the value of mod psi square, it will have a probability of collapsing there. So if you allow that, then you will find that it will collapse at other positions. See, it is collapsing at other positions. These are non-unitary processes. By the way, one thing I have to tell you, that normally the collapse happens to an eigenfunction of the observable. Now, in this case, the position is the observable. The eigenfunction of the position observable is a delta function. We could not do that because a delta function is not a differentiable function, and therefore further evolution would be non-computable. So we collapse it into a narrow Gaussian function. Okay, but you see the way it is evolving now. It is evolving in a combination of It's evolving combination of unitary evolution as well as non-unitary collapses, and the collapse is happening due to its interaction with the wall, but it's happening at other places governed by the Bonds rule. And our postulate 4 was everything remains the same, only R is now a random number between 0 and 1. In this case, the behavior is similar, only the R is not a constant. Okay. So you can see the collapses, right? Yeah. Now let's proceed. The question is, in this case, will there be sensitive dependence on initial condition? First, let us consider the case where there was no collapse. So we took two nearby initial wave packets, and we found that in this case there is no sensitive dependence. If there is a collapse postulate 1, in that case it actually collapses whenever the condition is satisfied. It collapses to the wall, and when it collapses to the wall, next instant it still satisfies the condition, and therefore it stays put there, and that is why you see that it is 0. Now collapse postulate 2 is where R is not constant, and therefore it does oscillate. But in this case also you do not see a sensitive dependence on initial condition. But in the postulate 3 and 4, where you are allowing the wave function to collapse according to the Bonds rule, here you do see signatures of sensitive dependence on initial condition. It is not deterministic chaos, because the system itself has a stochastic character. It is not deterministic. And because of that, we could not apply the 0-1 test, because 0-1 test is applicable only to deterministic systems. But we can see that the behavior is aperiodic, and there is sensitive dependence on initial condition. The question is that if you have this kind of many postulates, you do not know which one is correct, then any good work should tell how to distinguish between them in terms of observable quantities, in terms of what can possibly be experimentally verified, experimentally tested. Now, in this system, two very clear observable quantities are the energy and the position. So we took a look at that. What would be the expectation value of that? Now, when we did that, we found that if there is no collapse, we are not allowing the collapse, then this is the distribution of the eigenvalues. These are the eigenvalue numbers. So this particular eigenvalue has the highest probability, the others less, so on and so forth. So this is something that is tested. Now, if you have the postulate 1 or 2, then the average is higher. So the average occurs at higher energy. And if you consider postulate 3 and 4, the average occurs at lower energies. And I have never done experiments in this area, but I would assume that some experimentalists will take a look at it. And if we find the system, the unitary evolution is easily computable, and you can easily predict what the energy behavior should be, and if you find that, then we know that in such a system there is no collapse. If you find that you are getting an energy value that are higher than that, you know that either of postulate 1 or 2 would be applicable. If it is lower than that, you know that the postulate 3 or 4 will be applicable. And these are the expected energy values. If you look at the position space, then there will be two humps. This is the case where there is no collapse. There will be two humps because it's oscillating. It's stopping there, again oscillating this side. So there will be larger time when it's spent here, another larger time when it's spent there. There will be two humps, but asymmetric humps. When you consider the collapse cases, in this case, as I told you, that it will just collapse once and then it will stay put there. But in other cases also you see two humps, but the character of the humps are different, and the naturally these may also be something that is testable You can have, in some cases, you have asymmetric humps. In some cases, you have the mean values different. So these might be another testable criteria of. But my assumption is that this will provide a better testable criteria of which collapse postulate is right. One thing is noticeable is that if one of these collapse postulates comes out to be right, then it will contradict what you study in your textbooks. Because in your textbooks you study, when does the wave function collapse? When you make an observation, when a measurement is made. But here there is something that is left to itself. So a thing left to itself, if that has collapse phenomenon inside it, that will throw some light on the event of collapse. As John Bell said, the collapse should actually be occurring all around us all the time, because it is inconceivable that the world was evolving without any collapse till a human being appeared, first time making an observation of a quantum system, and then it collapsed. This is inconceivable. So there should be collapses happening all around, but we don't know the mechanism of that. This might provide a clue to that mechanism. So let us go to the conclusions. I'm almost done. For the unforced and undamped system, we found that the dynamics is aperiodic but not chaotic, but there is a finite number of frequency components. When it is forced and undamped, then the dynamics has signatures of strange non-chaotic orbit, and there are infinitely many discrete frequency components. If it is forced and damped, then the dynamics is aperiodic but not chaotic, but there is a drastic reduction in the number of frequency components. And finally, when you consider the soft impact with collapse, we find that it is aperiodic, but it has sensitive dependence on initial condition. And the postulates on wave function collapse, we obtain some kind of a testable predictions out of that. Thank you.
Thank you, sir. Thank you. So it's time for questions, suggestions, clarifications.
Yeah, so this is, yeah, Professor is asking. Yeah, definitely.
Oh, maybe.
Muruganandam, go ahead, please.
Yeah. Hi.
Hi.
Are you hearing me? Yes.
Yes.
Actually, I have a small doubt. Actually, so you are talking about this SNA. So the signature of SNA in the same non-chaotic attractor in this system what you are discussing.
Yeah.
Right. But is there any other way to confirm it? Because it was only based on this 0-1 test, right?
Well, this is where I would seek your advice, because you people are more expert on SNAs, and this is the first work on SNA that I have done. So you would be able to tell. But yes, 0-1 test is one.
Okay.
Frequencies, frequency components behaving in a fractal way is another.
Okay. Yeah.
These two signatures we have got.
Okay.
But if you advise me to look at something more, I would be glad to.
Oh, okay. So that's why I'm passing, because I don't know whether it's possible to do something else like.
No, there are two more ways, Muruganandam, isn't it? There are two more ways you can test the SNA, right?
Yeah, no, there are many actually. There are many tests. Applying to this method is probably we can use this OTOC type of measure, which I mean out of time or time order correlators actually. This could help some extent. We will see whether. Yeah, that's just curiosity I'm asking.
So you are suggesting OTOC, is it?
Yeah, probably, because this has a very nice intermittent spreading at this, which we noticed actually.
Okay.
Yeah, there is one possibility. Okay, I'm just, I don't know whether it will work or not, but how we are going to implement, and probably the There are some more tests, but yeah, we have to see the exact what is the data we have and how we are doing that. We have to see that.
Okay.
Okay, thank you. It was a nice.
Sir, there is one question in the chat box. The student is asking.
Oh, I didn't get the chat box.
Are you able to?
Can you just okay? Yeah, sir. Can the pulsing in laser cavity be studied to understand such quantum oscillator as experimental model to some extent? Well, I am not an experimentalist in this field. Actually, I am an experimentalist, but not in this field. So I really do not know. I have to consult experimentalists on this, whether these things can be tested using pulse lasers. Yes, I do not know that yet. I'm looking for experimentalists to throw some light on that.
Yeah, so Mitra, so I have a few questions. So none of these cases shows chaos in the, I mean, as you have presented today. That seems to be somewhat different from what you have been saying earlier. So earlier you have, I remember you were saying that in some cases you have observed chaos, particularly with forcing and damping.
Yes.
Now you have changed your opinion on that?
Yes.
Retested.
What happened was earlier our 0-1 test results were showing values close to 1. But now we find that happens only for some, not all, and most cases no. And so what has changed is basically we have redone the 0-1 test and we found that some of our earlier tests were erroneous. So we have changed that, we have corrected that. So my opinion now is that in the case of the soft impact oscillator, where you have a possibility of collapse, that is where you can have aperiodicity as well as sensitive dependence on initial condition.
No, but in the quantum case, why do you expect sensitive dependence on initial conditions?
Where?
Because after all, the Schrodinger equation is a linear.
No. So yeah, Schrodinger equation is linear. So if it is evolving only as per the Schrodinger equation, there cannot be any sensitive dependence on initial condition.
Yes.
Only when there is non-unitary evolution, as collapse processes are, then we would expect there can be any sensitive dependence on initial condition. Theoretically, that's what my understanding would be. Earlier, we were somewhat numerically getting signatures of one value in the 0-1 test. That's why we said earlier. But now I have some doubt about that result. So I did not present it that way. I changed my position.
Okay, so where does this non-unitary evolution comes in the case
Collapse.
of
Only when there is a collapse of the wave function.
why? Because of the randomness or what?
No, collapse of the wave function would happen when the wall makes an observation of the position of the this thing, and it will collapse either at the position of the wall or depending on the Bond's rule, wherever it is more probable to be there. But it will collapse there. So collapse process is a non-unitary process. Collapse of the wave function is a non-unitary process. So now we have an evolution of a quantum system which is nonlinear, because the collapse process is nonlinear. So far, every study on quantum systems assumed that quantum mechanics is linear.
Yes.
But the moment you introduce the possibility of a collapse of a wave function, it is a nonlinear evolution. Or I would say linear evolution punctuated by discrete collapse events which are nonlinear.
Maybe you should look for some other signatures, because in quantum chaos, in the wave function, there are other signatures one looks for.
Normally, the eigenvalue statistics.
Yeah, quantum, eigenfunction also, they look for certain crossings or some other structures. I'm not sure whether sensitive dependence is a possible signature, but you have to check. What about the energy levels of the undamped, unforced impact oscillators? Have you?
Yes, the energy levels are actually very similar. I have not put that slide here, but they are very similar to a normal harmonic oscillator. Only when it starts for the lower energy levels, they are the same. Only at the higher energy level, they diverge. So you have got a single a straight line for the normal harmonic oscillator. It is harmonic. It's another straight line with a different slope. That's all.
Okay.
So the eigenvalue difference statistics does not show up any important information.
Okay.
Because it is a straight line.
Yeah, very nice. Okay. Okay. Thank you very much. It was an enjoyable talk.
Yeah.
Professor Sai, you can go ahead. Yeah.
Yes.
No, Professor Muruganathan, if you want to.
No, Muruganathan, you want unmute.
No, it's okay. I was
okay.
just thinking of this paper who pointed out actually. That's okay. Fine. You just go ahead. Okay, fine.
Hello, everyone. Hello, Professor Shomitra. It's a great pleasure to meet you. We've never met, but of course, I know your work. So I just have a couple of questions, Professor Shomitra, if you'll allow me the permission to ask you this. So the first is basically the most immediate thing. I hadn't, to be honest, hadn't heard of impact oscillators. So this is very fascinating what you mentioned. But the immediate thing that comes to mind is hardcore bosons. And so I was just wondering if you have made contact with the literature on hardcore bosons, because I don't know that literature too well.
Can you say that again? With what?
Hardcore bosons. So essentially, they're models of fermions where you basically just have hard spheres and they can't cross each other, they can't pass each other. So there is a lot of quantum mechanics that's been done on hardcore bosons.
Okay.
Okay, I can drop you a mail on this.
Drop me a mail with some references. I'll take a look at that.
The second question that I wanted to ask was in your first part of the talk where you had the quantum impact oscillator. I couldn't help but notice that the Wiener function is positive semi-definite. You never needed a minus on the axis on any of your, and so this is quite interesting, isn't it? Because one of the kind of things that I would think of immediately from a quantum optics perspective, for instance, one of the curiosities that I would have with a problem like this is, can I start with a Wiener function which only has positive parts, which implies, I'm just saying this for the students, which implies that you can model it with the local hidden variable theory. You can just think of it as classical mechanics of a probability distribution. Whether you can start that way and basically then go into a regime where basically you have a non-classical behavior. So what I wanted to ask you
was an example of that.
Right? No, I have. There are many examples of that in literature.
In my talk, I showed that we started from a situation where it was positive, and it evolved into some negative parts. So,
did it? Could you just show me that figure again? Because I somehow seem to have missed this.
Well, let me see.
Because I was looking always for the color bar on your Wiener function. Sorry, I'm not ignoring you. My camera is over here. My screen is over here. So. My screen is over there.
How do I go to this presentation?
I can see your presentation. No, you don't have to go into presentation mode even. You can just maybe just pull up. It's okay. I mean, if you have a paper on this, I can look it up.
In my screen,
I can see main1.pdf in the Adobe Acrobat Reader. So if you just click on the correct section, it'll take us there. I think the Wiener distribution section. I can even see it.
Okay, I'll just go there.
Aha.
For example, here it starts from a perfectly positive distribution.
Yeah, no, but if you look at the color bar goes from 0 to 0.4.
No, go here. For example, here it does go below the 0. Yeah.
Below the zero is in the value of the Wigner function
Yeah,
becomes negative.
you do not see it here because it's
Okay.
viewed from the top.
Okay.
But yes, I can tell you that it does go below.
Okay, that's interesting actually, because it means that it generates non-classicality for whatever it's worth. So I just wanted to ask just one or two more questions, if I.
Yeah.
One is basically when you went to the section on the soft impact oscillator, what you did was you replaced it with measurements. But what you had actually shown, the diagram that you had shown was two harmonic oscillators, one with a much larger spring constant than the other. This is not the same thing as measurements, no? I mean, this is just an anharmonic oscillator, if you will. I mean, it's two harmonic oscillator, which is not the same thing. I mean, so I just wanted to. There's some transition that you made from essentially an anharmonic oscillator to a measurement based, where you basically just replace the soft oscillator with a probabilistic measure. I mean, the four postulates. But
Yes.
where did you make that transition?
Yeah.
Or what is the?
You might say that the system we have can be considered as a couple of harmonic oscillators with the possibility of making a impact. You might also say that the other one is a classical system, or say sort of a container in which the particle is released, but the container has a possibility of sort of moving. Okay. If it is classical system, today I have presented the situation only when it is a classical system which observes the particle and therefore the particle's wave function collapses. You can also imagine that both are quantum systems, both are quantum particles, and therefore when they, there are two possibilities. The usual quantum mechanism will say nothing will happen. There will be no collapse. But you might say that fine, but if they meet each other, they know that they are at the same position, that's in some way collapse. And therefore, let their collapse be. The trouble with that is that the collapse postulates that are there do not conserve energy. So if you allow that to happen, then the energy will keep on changing, and that's not the right way to do the physics. So we try to see how can we have a postulate on collapse which will conserve energy. I did not present that today, but that is another work that we have done. So what will be the outcome of that? What will be the experimentally testable outcome of that? Assuming that just a couple of harmonic oscillators which have possibility of looking at each other, interacting with each other, supposing that there is a possibility of a collapse, then what will be the experimentally testable prediction out of that? We have done that. But after working out, what will be the condition to be satisfied if the energy has to be conserved? I
just want to make one final comment on the problem of collapse. The problem is basically that any probability distribution that you show or probability density that you show, you cannot even obtain this without putting a probe at a, so if you think of this as basically a quantum particle or whatever, you can't even make this without putting a probe. And so the probe will induce a measurement model, which will bring with it a measurement model. So I think the Heisenberg cut problem, which is the thing that you're trying to address here, it doesn't go away. I mean, I don't see how it would go away. I think you would just have another version of it in basically any prediction that you make. How do I see this? It has to be, that is what I don't know. I just make this comment, but maybe we can talk about it offline.
Yeah, this is a rather difficult area because the usual quantum mechanics says that only when you make a measurement, then the wave function collapses.
I just want to make one last comment, which is that there are tons of measurement models that you can use. So there is models for continuous measurement, there is models for position measurement, and in fact, there is a lot of work by Kurt Jacobs, who I had the pleasure of working with at some point. And this gentleman, whose name will come back to me in a second now, his advisor, they basically showed that this continuous measurement models actually produce chaos. And in fact, they show quantum to classical transitions and chaos and all that behavior.
Rimini and Weber, they produced a continuous collapse model. Yes, GRW model as it is called. And there are other collapse postulates.
Yes. This one doesn't require. It's a more engineering approach. It doesn't require any gravity or anything crazy.
No, there is the gravity-induced collapse. There is a spontaneous collapse by Ghirardi, Rimini, Weber. We are saying that it is it is induced by some kind of interaction.
Sure.
Interaction with another body. So it's sort of a different take on the problem.
Sure. Thank you.
Sir, I have one small question. Have you tried with the pilot wave theory to understand these collapses?
Yes. We are now looking at that, but we have not yet taken a complete look at that. So I may not be able to answer your question. Maybe 1 year later I will be able to.
Yeah, because Bohm theory is powerful. People say.
Yes, exactly. That's why we are interested in the Bohm theory, pilot wave theory.
Yeah.
And in fact, we are also setting up an experiment of oil droplets with which the pilot wave theory is sometimes tested.
Yeah.
All experimental observations have to agree, no? I mean, independent of which interpretation of quantum mechanics, all experimental observations have to agree. So, how would you even test this process until? I mean,
So actually, I'm seeing papers relating chaos with the pilot wave theory nowadays.
Oh, I see.
Yeah.
I see. So that's the perspective you're taking. I see. Okay.
Yeah, we are looking at the pilot wave theory. Yes.
So questions from students? I think they're a bit hesitating.
Yeah, that happens. Our students also are hesitant sometimes.
Okay. If I'm not seeing it.
Sir, one more question.
Please, Venkatesan, go ahead.
I have found literature that in classical, if you have a strange non-chaotic attractor, the corresponding quantum part they have shown Anderson localization phenomena. Is there any relations between that?
Oh, I do not know that, because in this case, the classical system does not show strange non-chaotic attractor.
Okay.
In this system, in one case, when there is no forcing, no damping, the classical system is periodic.
Okay.
When it's forcing, the classical system is chaotic.
Okay.
And we are finding that its quantum domain, it is strange non-chaotic orbit.
Okay. Thank you, sir. Thank you.
So, any other questions from the audience? So, if not, let us wind up the session.
I have one question. Sir, good afternoon.
Chandra, yes.
So what happened if we consider the nonlinear potential in the hard impact classical systems? Can we expect the sensitive dependence behavior on quantum analog, or if we consider nonlinear potential?
Well, this is what I showed. That means you do have a hard wall terminating a harmonic oscillator potential. Okay. Now, in that case, the wave function has zero value at the wall because it is infinite. So the probability of finding the particle at the wall is 0. Okay, so there is no possibility of collapse. And therefore, it is completely unitary evolution following the Schrodinger equation. And if it is a unitary evolution following the Schrodinger equation, I don't think there can be any sensitive dependence on initial condition. So I would not anticipate a sensitive dependence on initial condition in that case.
Thanks.
But we do see strange non-chaotic attractors. That's what the take-home message of our story is. Even if it's not chaos, there is strange non-chaotic attractors.
So, any other questions? Let me wait for a second or two so that I. Okay, sir. Yeah, I'm not seeing any questions. I'm not getting any questions. So let us wind up the session by thanking Professor Sumitra Banerjee for giving a very wonderful talk on both classical and quantum aspects of an oscillator, impact oscillator. So thank you, sir. Thank you very much for accepting our invitation and giving a lecture in this forum. Thank you.
Thank you. Thank you for inviting me.
Nothing. I will write to you the other formalities by email, sir.
Okay. And those who say that they have come across papers that might be interesting to our work or of relevant to our work, please send me.
Yeah. You know, Professor Sai is working in IIT Bombay. He works on quantum synchronization.
Yeah. One of the things that I look forward to in this talk is this interaction. I may not have come across a paper, you may have. So please send me.
Sure, absolutely.
And Muruganam, please do send me papers on the test of SNA.
Oh,
So
yeah,
that
I'll try. Yeah.
Sir,
Sure.
Professor Muruganandam and myself has done a characterization of this SNA by OTOC.
yeah. Please do send me. And Professor Sai, please send me the papers on the what do you say, hard bosons.
Yes, absolutely. Yeah.
Yeah.
Thank you very much.
Thank you.
Thank you, sir. Thank you very much.
Bye.
Bye.